So it's my honor, this is the third talk, it's my honor to introduce our speaker, Professor John Cassano from CU Boulder. So he's a professor at ATOC, which is Atmospheric Oceanic Science. So where I worked there for 5 years before moving here. Now, as you see the title here, now John is also the lead scientist for the NIST, right? National Snow and Ice Data Center. So you know he's dealing with the colder stuff there. So now the one thing, so really making me admired to the John's work is everything's cold. I grew up in the warm place in China, so the cold place is so pressure for me. So, but after spending 4 years, 4 months, not around 4 years, right? Just spent many years on 4 months at Arctis. This year, I really appreciate people try to do their best for their life or science there. But another thing is that there's so many exciting things. Right? Then I'm looking at where John's career path. I kind of get appreciated with his dedication for code. So he grew up from Long Island, not cold enough. Then go to Montana for bachelor's degree, not cold enough, go to Wisconsin, right? Wisconsin, they have long winter, but it's not necessarily a cold place. So then he got a PhD from University of Wyoming, where I spent 15 years as faculty. I know it was a cold in general, right? But my other colleague calmed down me that, yeah, so 20, 30 years ago, even colder. That's what John experienced. Right? So he liked coding, enjoys science of the cold place. So he was talking about a lot of interesting and exciting thing about the code boundary there. So, okay, take over.
Thank you. Yeah, so I'm really happy to be here. Like Ben said, I grew up on Long Island, but haven't lived here in more than 30 years. And I've been to lots of cold places. My research is mostly focused on polar weather and climate. Today I'm going to talk about the polar boundary layer and show you sort of a range of boundary layer conditions. So for the seminar today, I'll just give you a quick overview of what types of work my group does. But today's talk is going to be all about boundary layer work that we do. I have 3 topics. I'll talk about Antarctic boundary layer studies that we've been working on, and then I'll end with an Arctic and a subarctic boundary layer project as well. So my group's research, you know, when I meet prospective graduate students or things like that, and they ask what I do, the way I describe what we do is that we're interested in how the atmosphere interacts with whatever is underneath it in the polar climate system. So that whether that's sea ice or ocean or land or ice sheets. And then to do that, we take part in observational field campaigns where we make measurements in the lower atmosphere and try to understand how it's interacting with that lower surface. We also have an interest in polar weather, synoptic and mesoscale processes, and the impact they have in shaping polar climate system. And then maybe a bit unusually, my group also spends a lot of time doing weather and climate modeling. And we've developed a regional coupled Arctic system model. The middle picture on the right shows the domain that we simulated. So we have an atmospheric model coupled to ocean and sea ice models, and then land and hydrology, and occasionally ice sheet models as well. But today I want to talk about just the boundary layer work that we do. Most of you already know, the boundary layer is the bottom part of the atmosphere. It's the turbulent part of the atmosphere. It's where the atmosphere interacts directly with whatever the surface happens to be. Depending on where you are and what time of year, the boundary layer can be as shallow as a few meters if you go to Antarctica in the middle of winter, and it can be, you know, several kilometers deep. when I was a master's student at the University of Wisconsin, I took a boundary layer class from Roland Stell. He wrote an excellent boundary layer textbook back in the 1980s. And the first day of that class, he talked about, why should you care about the boundary layer? And it has stuck with me ever since. We live in the boundary layer. And so our perception of how the atmosphere behaves is shaped by the fact that we live in that part of the atmosphere. So things like the fact that temperatures go up and down every day, right? It's cold in the morning, warm in the afternoon. That's a boundary layer process. That's not true if you get outside of the boundary layer. When you think about wind, the thing that comes to mind is that it's gusting. That's the turbulence of the boundary layer. Again, that's not what you see if you're outside of the boundary layer. And then things like air pollution are inherently a boundary layer problem. So it's clearly an important part of atmospheric science. But for my research, the reason I care about it is it's where the atmosphere interacts with that underlying surface, sea ice or ice sheets or oceans or whatever it may be. So if I want to understand that coupled Arctic or polar climate system, I have to understand the boundary layer. Okay. So the first boundary layer topic I'm going to talk about today is work we did back in 2009 and 2012. We were looking at cold air outbreaks over Terra Nova Bay in Antarctica. So we used uncrewed aerial systems drones made by a company called Aeroson. Aeroson developed these drones to fly into tropical cyclones, but they were also ideal for the work that we wanted to do in Antarctica, which was to look at cold air draining off of the Antarctic continent and then blowing out over the adjacent sea ice and ocean. And we chose this place called Terra Nova Bay to do this work because it's an area that's impacted by strong katabatic winds, which I'll say what those are in a minute. It's an area where there's a recurring polynya, and I'll define what that is in a minute. And then the combination of those two things make it important in the polar climate system because the winds and the polynya result in generation of Antarctic bottom water, which drives global ocean circulation, or is an important component of global ocean circulation. When we went to Terra Nova Bay to make these measurements, end of the winter in 2009 and 2012, it was the first time that anyone had made in-situ measurements over this polynya environment. We also were the first group to do drone flights in Antarctica in the winter, along with a group at the British Antarctic Survey that was doing flights that same winter as us. So we were sort of pushing the edge of what we could do. The background picture is a photograph we took from our drone. The image is about 100 meters across, and it's sea ice, pancake ice, so you see little pancake-shaped flows, and then some thicker sea ice floating out over the ocean next to the Antarctic continent. So katabatic winds, if you haven't heard of them before, they're basically a density current. So the Antarctic continent, if you don't know the geography of it, just imagine flipping a bowl upside down. It's a big domed ice sheet. The elevations in the interior of the continent, the plateau, are above 3,000 meters. It gets really, really cold there. That cold air is dense. And as a result of the slope of that ice sheet, that dense air basically slides downhill just like water flows downhill and forms what are called katabatic winds. So these are just negatively buoyant drainage winds flowing off of the Antarctic continent. The map on the left shows the wintertime streamlines of the Antarctic continent. The highest elevation on the continent is here. You see those streamlines spreading out. It's that cold air draining away. The topography of the ice sheet channels the cold air into preferred locations. So there's a place here on the East Antarctic coast, Cape Denison. Some of the early Antarctic explorers visited these places with strong winds because the winds blow the sea ice away from the coast. It made it easy for them to get their sailing ships in. So Douglas Mawson wrote a really interesting account called The Home of the Blizzard about living through these katabatic winds in the winter. Terra Nova Bay is right here, another place where those katabatic wind streamlines converge. As a result of those winds converging like that, you can get consistently hurricane force winds blowing for most of the winter in places like this. So it's a very dynamically interesting place. Those katabatic winds do a few different things that are important. So here, I want to tell you about polynyas. So we're looking at The Antarctic continent is off on the edge here. We have the sloping ice sheet. We have cold katabatic winds that are draining down, sometimes as strong as hurricane force. In the winter, all of the ocean around Antarctica is covered by sea ice. It's cold, the ocean freezes. But those strong winds force the sea ice away from the coast. So they mechanically push the ice away, exposing open water. This air coming off the continent is, anywhere from -20 to -40 degrees Celsius. So that cold air blowing over open water causes tremendous upward turbulent heat fluxes. It extracts energy from the ocean. The ocean is already at its freezing point, -1.8 degrees Celsius for salt water. As you extract energy from that water that's at the freezing point, it generates new ice. And so the winds are pushing the ice away. They're extracting heat from the ocean and generating new sea ice, which gets pushed away. When you freeze ocean water, the fresh water part of that freezes into sea ice and the salt is left behind. So what you're left with is the coldest, saltiest water in the world ocean being formed in this area of where the sea ice has been blown away. This area of open water is called the Plinia. That cold, salty water then drains or sinks into the ocean convectively down to the bottom and forms Antarctic bottom water. The picture on the left is a visible satellite image. The Antarctic continent is over here. The coastline is right about here. There's some floating ice and ice shelf here, that's glacier ice. And then everything on this side of the image is sea ice, except for here in Terra Nova Bay where the katabatic winds are funneled down and they've blown the sea ice out. But you can actually see streamers of new ice being formed as that cold air blows over the warm water. So this is the environment that we went to. We used an Aerosonde uncrewed aerial system. These were designed to fly into tropical cyclones. We were flying in hurricane force winds, except much colder, but it was an ideal platform for us to use. The Aerosonde's a moderately sized drone, 3.6 meter wingspan, weighs about 20 kilograms. We carry a few kilograms of science instruments. The reason that we use Aerosondes, though, is that they could fly long distances. We configured them to be able to fly about 1,000-kilometer missions over a period of about 19 hours. Fly around 50 knots. We communicated with radio when it was in line of sight, but we mostly flew beyond line of sight, so we used an Iridium satellite phone and modem to talk to it. We programmed the planes to do pre-programmed flight plans, but we could change that depending on what we were observing. And we were basically measuring atmospheric state, temperature, pressure, humidity, and wind. So we had two campaigns, end of Antarctic winter, 2009 and 2012. We flew about 300 flight hours over 30 flights. All right, I want to show you a video of how the Aerosonde takes off and lands. So you see that Aerosonde is mounted on the back of a pickup truck. For the Aerosonde to take off, it needs to be traveling about 50 miles an hour. And so what you do is you take this pickup truck, you drive it down some smooth ice on Antarctica, get up to about 50 miles an hour. When the truck gets up to that speed, the plane lifts out of the cradle, takes off, motor turns on, and it goes on its way for its 15, 19-hour mission. Let's watch a video of this happening. So the Aerosonde is sitting right on top here. And then the person standing here actually has just a remote control that he'll manually fly the plane when it takes off before it goes into autonomous mode. So not when I did this mission. Oh, actually 2012, my daughter was 3 years old. I had a Skype call with her, and I was talking to her one day from Antarctica, and I was telling her how cold it was. She's like, "That's not cold, it's sunny, it looks nice out." I assure you it was cold. This flight was probably about -40 degrees when we did the launch. And then the landing, so the Aerosonde is here. So after flying for 15 hours and going up to Terra Nova Bay, which is about 300 kilometers away from where we launched, the plane comes back. It doesn't have landing gear, it lands on its belly. So you're gonna watch things gonna circle around and then land. This is an ice runway where manned aircraft land during the summer. Air is right here.
So it's gasoline powered, I assume.
It is. This one is. Yep. And it doesn't really like the cold very much. We broke the generator belt on one flight. We had a few different problems with cold. Not to mention for the people that were flying it.
-40 batteries.
Yes. At -40, everything is hard. Okay. So that's the tool we used. The flights that we did typically followed a path that looked like this. So Antarctica, the United States Antarctic Program has its biggest base at McMurdo Station. It's right here on the southwestern tip of Ross Island. There's a ice runway here where manned aircraft fly in during the summer. That was where we based all of our Aerosonde flights. So we take off from Pegasus, we fly north up across McMurdo Sound, the western Ross Sea. This is a floating bit of Antarctic ice sheet, the Drygalski ice tongue. Then we fly up into Terranova Bay, fly around, make measurements for 5 or 6 hours, and then fly back and land. So that was a typical campaign. Features that you can see in this plot of winds, and these are about 100 meters. Strong winds in Terranova Bay. Here the winds are something like upper 20 meter per second range. So not a terribly windy day in Terranova Bay in the winter. You can see a shear vortex south of Terranova Bay, driven by that low-level jet of katabatic winds coming out. And then broadly, the meteorology in this part of Antarctica is dominated by southerly winds coming across the Ross Ice Shelf. Ross Island is the southernmost active volcano in the world. It rises up above 4,000 meters. Those southerly winds hit Ross Island and split around. And you can see that split flow of the easterly winds coming over this low peninsula, the Hut Point Peninsula. So a lot of interesting atmospheric dynamics to look at. I'll show you a sequence of plots showing the winds up in Terranova Bay and then a satellite image at about the same time for a bunch of flights we did in September of 2012. And the way that we do our flights, we come in across Drygalski ice tongue, we fly right along the coast. So this is all Antarctica and this is all ocean over here. We fly right along the coast, see where the strongest winds are located, and then we do sort of a sawtooth pattern to map the extent of the winds. Here, the winds were getting up in the upper 20 meter per second range. In the satellite image, this is all permanent ice, the Antarctic continent. This is all sea ice, and you can see the Pleiade just starting to open up at the coast as those strong winds come offshore. The next day we went back, the winds now are up around 35 meters per second, so hurricane force winds. The Pleiade, the sea ice is starting to move out. You can see some low convective clouds forming from the big upward central and latent heat fluxes. 3 days later, the winds are still blowing something like 35 meters per second. Very persistent, strong winds here. The Pleiade is now wide open. This distance is something like 40 kilometers. So we push all that sea ice out. And then 5 days after the first flight, the Pleiade is still open. You see some convective clouds in the visible satellite image. And the winds are still blowing better than 25, 30 meters per second. So really a phenomenal location meteorologically. Things that we were doing in terms of the science. So as we would fly the plane, after we did our sawtooth pattern and mapped out what the wind field looked like, we would fly parallel to the strongest winds away from the coast to see how the atmospheric state was changing. And so the distance on this scale goes from the coast out to about 40 kilometers. And then we can see the air temperature, and it's warming up from coming off the continent at minus 21 degrees Celsius. It warms up over time. That's the heat coming out of the ocean. The dew point temperature rises. That's the moisture being evaporated out of the ocean. And then the wind speeds here flowing around 23 meters per second, slowing over time, reflecting the atmospheric momentum being deposited into the sea ice, which is what pushes the ice away. So this really captures how the atmosphere is interacting with this Pleiade environment. And then one thing we did is we would do spiral profiles at several locations about every 10 or 15 kilometers from the coast downwind to see how the atmospheric state changed. The profiles here, the blue one is at the coast, then green, then orange, and then red. And so what you see is that downstream warming, which you expect because you have an upward sensible heat flux. The top of the boundary layer is about 200 meters at the coast, then it deepens to a bit more than 400 meters. But with these measurements of the depth and temperature of the boundary layer and how it changes over time, and the fact that we're sampling in a sort of semi-Lagrangian sense by flying directly with the wind, we estimated how much heat was coming out of the ocean and into the atmosphere between pairs of profiles based on how much they warmed or cooled. And you can see in this case, we had the maximum heat flux between the green and the orange profile. Average over that 10 kilometers of about 580 watts per meter squared. That's a lot of energy going into the Antarctic atmosphere. End of the winter, when the sun is basically down, you don't have a lot of energy, other energy sources. So this is a pretty important process. And of course, that energy coming out is what allows the sea ice to freeze that generates that cold, salty water. And then a few images from the aerosol. We had a downward pointing camera on the bottom. Each of these images is about 100 kilometers across. Here you can see large waves generated by those strong winds, white hats on the top, sea spray blowing off of them, and then streamers of frazzle sea ice. So that's the newest sea ice that's just forming, being aligned with the wind. So the wind is from top left to bottom right in this image. As you get further downstream, those little thin needles of ice start to come together and form pancakes. So this is pancake ice. These are each, like a meter-ish across. And you can see the swell of the ocean underneath these from the momentum that was transferred into the ocean. Okay, so that was Terra Nova Bay. That was an interesting place to go, a lot of interesting science to do. But the aerosols were expensive. We crashed a few of them because we were flying in pretty bad conditions. I decided that flying something small and simple would be nice too, that didn't require a team of pilots and engineers to maintain. And so I started flying these SoMAS UAS. So SoMAS stands for Small Unmanned Meteorological Observer. They're made by a couple of engineers in Germany that were RC model plane hobbyists. And they had interacted with some folks at the University of Bergen to build an autopilot and put instruments on basically a model RC plane that you could then fly wherever you want to fly. So I took my SoMAS to Antarctica and did a bunch of measurements with those. We've done a bunch of campaigns with the SoMAS in Antarctica. So once again, here's Ross Island. To orient you, here's an overview map of Antarctica. If you go straight north, you run into New Zealand. This is the Antarctic Peninsula. You go north from there, you hit South America. So the main US base, McMurdo Station, is right here on the southwestern edge of Ross Island. South is up on this map. We did a bunch of campaigns at the two runways. There's a snow runway, Williams Field, and ice runway, Pegasus, by McMurdo, so we did a lot of flights there. We have a 30-meter automatic weather station tower that's been in Antarctica now for more than a decade, making measurements of the bottom 30 meters of the atmosphere. We did a campaign out here, and then I did some work with the New Zealand Antarctic program in a place called Lake Bandit in Wright Valley. This part of Antarctica is one of the only places that is snow-free in the summer, called dry valleys. So that's an interesting environment. Oh, and then we also took part in a research cruise fall into winter in the Western Ross Sea. So we had a bunch of SoMAS flights off of the icebreaker. So the SoMAS is a very different drone than the Aerosondes. It's small, 0.8 meters, weighs a little more than half of a kilogram. It only flies for 30 minutes. It's battery powered. Makes the same measurements, so temperature, humidity, pressure, and wind. And usually we'd fly by just spiraling up and down to measure profiles of the atmosphere. We didn't need any real logistics for it. We don't need a pickup truck to drive 50 miles an hour to launch it. You just throw it by hand. Me and a graduate student usually go out to a field camp and we do flights and we fly, every couple of hours throughout the day to see how the boundary layer was evolving. This is me and a colleague from New Zealand doing a flight in the dry valleys. So this is one of those ice-free places in Antarctica. So I'm flying the plane with remote control, and then Marwan is going to launch it. Rather than the pickup truck, you just throw it, takes off. So you'll see it take off and then you'll see it land. Decidedly lower tech than SoMAS. But the environment here is such that we couldn't really bring anything logistically complex in. And just lands on a spelling, just like the aerosol does. So the SUMOs opened up for us the possibility of going to remote field camps and making measurements and observing above just the surface. So you go around Antarctica and there are weather stations, dotted all over the place that measure what's happening in the atmosphere right at the surface, but you don't have that information about the vertical structure of the atmosphere. So these small drones really open that up for us as an area of research. Here I am with one of my graduate students, myself. We have a ground control computer that communicates with the plane by a little radio modem. So we have ground control software on the laptop and a remote control. This camp, there were 3 of us at this camp. We were camping on the Ross Ice Shelf, which is an area about the size of France. And we were the only 3 people in that area the size of France doing our flights. So we go to some pretty remote places. The ground control computer, it looks just like a flight simulator. You can see a map showing you where the plane is, program information. You can put information up here about the temperature and winds and what it's measuring, information about the plane's status, battery, GPS. You can see the plane's orientation, and you can tell it to do whatever pre-programmed flights you want it to do. And the flights are about 30 minutes. The plane usually fly 1,000 meters up and down. It gets tiring standing with your head like that, so you lay on the ice and just watch it with a remote control next to you in case the plane decides to do something stupid. So I want to show you a few measurements that we made to show you the range of conditions that you can see in the Antarctic boundary layer. So these are flights we did at Pegasus Runway, late winter, really cold, surface temperatures around -40 degrees Celsius. I'll point out, so the scale here is 0 to 600 meters. This temperature inversion, right? It's 8 degrees Celsius over 30 meters of the atmosphere. Phenomenally strong vertical temperature gradients that you get in the stable boundary layer. I've plotted flights over a period of about 24 hours. And the thing that's striking is there's almost no change, right? You imagine making measurements here in Stony Brook over a 24-hour period, and you're going to see, temperature warming and cooling and doing all sorts of things. Antarctic winter is different. So very steady state. Very strong cold temperature inversion.
Is there sun at this time?
Yes, so the sun is up briefly, but it's really low in the sky. So there's almost no solar radiative forcing. Here's another set of flights. This is over, again, almost a 24-hour period. Almost no temperature change aloft, so 300 meters up, but very strong cooling at the surface. That was a function of clearing clouds. Here, another case with very sharp, shallow temperature inversion, warm air advection aloft, at 200 meters, but cooling at the surface, indicating how strongly decoupled the surface and the air above can be in these polar environments. And then this is a summer flight, a series of summer flights, again, over about a 24-hour period in the dry valleys. So these flights are early morning, like 7 a.m. Sun's up all the time, but there is a diurnal cycle. The sun's elevation rises and sinks during the day. Dry adiabatic lapse rate is here, indicating a convective profile. So we have a shallow convective boundary layer, less than 100 meters deep in the morning. And by afternoon, that's deepened to the top flight level that we could fly, which was 900 meters. So you can get deep convective boundary layers in contrast to those very strong, stable, shallow boundary layers that I showed you in the winter. So we've done lots of things thinking about the Antarctic boundary layer. One of my most recent PhD students decided that she would look at radiosonde profiles from manned sites across Antarctica. So she looked at 3 coastal locations: McMurdo Station, where I've done a lot of my fieldwork, Showa, a Japanese site, Neumayer, a German station, and then 2 interior sites: South Pole, which is 2,800 meters, and then Dome Sea, which is almost 4,000 meters in elevation. So very different environments. So she analyzed daily radiosonde profiles for multiple years from all of these sites to basically look at what is the range of stability that we see across the continent and across the annual cycle, and how does that differ depending on where we are. So in the end, she analyzed something around 20,000 radiosonde profiles. And to do that in an intelligent way, to make sense of all of this information rather than having her look at all of them individually, we used something called self-organizing maps, which is an artificial neural network technique for clustering data and doing it objectively. And so here's an example that Mackenzie, my student, had, where she said she asked the algorithm to identify 30 patterns that span the range of profile shapes seen in about 1,200 profiles from one of the sites. The profiles are plotted as potential temperature anomaly, so change in potential temperature from the surface, so the surface is always zero. They are always increasing, the atmosphere is stable all the time, and this is over the bottom 500 meters. So each one of these little figures is showing you potential temperature change with height in the bottom 500 meters of the atmosphere. So we did this we trained a self-organizing map for each of the 5 sites to see what the boundary layer looks like at each of those sites. And I'll show you an example for a coastal site, and I'll show you an interior site. So this is SOA. You can see the number of profiles we've had at these 3 different coastal sites and the time range. What you see when you look at this self-organizing map is a range of boundary layer stability situations. So the top left in this case, the average profile is almost constant potential temperature with height, so near neutral. If I go to the bottom right, we see very strong potential temperature increase with height, a stable boundary layer, near surface, surface-based inversion. Then we also see some profiles where there's weak stability near the surface, where potential temperature is not increasing very much, and then there's enhanced stability aloft. That was common in all of the coastal sites, that we saw this range from near neutral to relatively strongly stable, but with a lot of sort of weak stability near the surface and stronger stability aloft. If we go to the interior sites, they're different. Here, South Pole and Dome C, about 14,000 profiles. The scale for the potential temperature anomaly is different. The previous one went 0 to 15, this goes 0 to 40 Kelvin. The depth is still 0 to 500 meters. The profiles that the self-organizing map extracted or told us sort of help span the range of what we see in the data, really strongly stable. Big temperature increases, potential temperature increases with height. But we do get cases where the potential temperature doesn't increase very much with height. So moving towards a near neutral stratification, even in those interior sites. And then we also see this sort of layered structure with weak stability near the surface and then very strong stability some distance above the surface. So the self-organizing maps were nice because they let us visualize this about 20,000 radiosonde profiles and let us sort of see what exists in this data set. But because we trained separate self-organizing maps for each of the sites, we couldn't really do any quantitative comparison between them. And so what Mackenzie and another one of my students decided to do was that they would define stability regimes. And they would classify stability from near neutral, where potential temperature increases less than 0.5 Kelvin over 100 meters, to extremely strong and stable, potential temperature increasing more than 30 Kelvin per 100 meters. And they define stability near the surface, so 20 to 50 meters. 20 meters was the lowest reliable height from the radiosondes. And we just found that looking over 30 meters gave us a good sense of the stability. So we did this near the surface, and then we found the top of the boundary layer in each profile and went from the top of the boundary layer to the 500 meters, the top height that we were interested in, and classified the stability there. And so we came up with a total of 20 stability regimes that we could then define for any radiosonde observation at any of our sites across Antarctica. One of my other students did it for Arctic data, but it could be done anywhere you wanted to. And here I'm just showing some of the basic stability regimes. So from near neutral to extremely strongly stable. The blue line is a potential temperature anomaly. That's the axis on the top. Here, The 0 is at the top, but it's still just telling you how is potential temperature changing with height. So near neutral, potential temperature anomaly is nearly constant with height. Extremely strongly stable, the potential temperature anomaly change or potential temperature changes about 30 Kelvin over the depth. And you can see, weak stability, that's temperature increasing, not as strong, two varying different types. So these were the different stability regimes that they identified. And then Mackenzie said, all right, well, let's see how often these different stability regimes occur at different sites. This bar graph is ordered from weakest stability, near neutral. This is a very shallow, well-mixed boundary layer. Weak stability, moderate, strong, very strong, and extremely strong stability. The bars are the 5 sites. The 2 blue ones are the interior sites, Dome Sea and South Pole, and the green and yellow and orange are the 3 coastal sites. So what you see is near neutral, very shallow, well-mixed boundary layers occur a lot of the time at the coastal sites and not very often in the interior. And they occur about 50% of the time. So when you think of the Antarctic and you think, oh, the boundary layer is stable all the time, it's not. When you go to these coastal sites, weak stability is as common as anything. Moderate stability regimes occur about the same frequency at all of the sites, which we thought was interesting. And then the strong to extremely strong stabilities are dominated by the interior sites, where that very strong stability occurs more than 50% of the time. This is the near surface stability, not the stability above the boundary layer. And then the next thing that Mackenzie did is said, well, can we see what drives the different stability? And 2 things that drive near surface stability is the radiation budget. And for polar regions, this long wave radiation that is really important most of the year. So she looked at how does downwell and long wave radiation change as I go from these weakest stabilities to the strongest stabilities across the different sites. And the other thing that drives near surface stability is near surface wind speed, which generates turbulence and mechanical mixing. And the expectation is that weak stability is favored by strong winds because that generates turbulence and mixes the atmosphere, and strong stability occurs with light winds. So Mackenzie calculated the average downwell and long wave radiation going from the near neutral to extremely strongly stable for the 5 sites. When she showed me this graph, I was really impressed at how uniform the trend in downwell and long wave radiation is as you go to increasing stability, regardless of what site you're at, given the very different physical environments of those interior versus coastal sites. But it's something like 60 or 70 watts per meter squared difference in downwell and long wave radiation that takes you from a near neutral stratification to one where the potential temperature is increasing 30K over 100-meter height.
Is this long wave calculated or measured?
It's measured by radiometers at the surface. The wind speed didn't behave near as cleanly as we expected. Although if you look from the weak stability to extremely strong stability, most of the sites have a decreasing wind speed trend as stability increases, as we'd expected. But there's a lot more subtlety going on there that don't really have time to talk about today. And then the last thing I want to show with this work that Mackenzie did before, I think the last 10 or 15 minutes to talk about Arctic stuff, is she looked at not just the near surface stability, but also the stability above the boundary layer, found whichever of those stabilities was the greatest, and calculated how often each of those stability regimes occurred in that bottom 500 meters. And here what you see is that the near neutral cases are very uncommon. So even though near neutral stability occurs a lot near the surface at the coastal sites, once you get just above the top of the boundary layer, the stability becomes much stronger. But weak stability and moderate stability tend to dominate the lower part of the atmosphere at the coastal sites. Strong stability is common at all of the sites, and then the very strong and extremely strong is only at the coastal sites. So strong stability and stronger occurs more than 80% of the time at the interior sites, whereas weak and moderate stability is something like 60 to 80% of the time at the coastal sites. So again, very different stability regimes at these 2 different types of places on the Antarctic continent. Okay. I also do Arctic work. So this is work that I was doing with another one of my students, Gina. up on the Arctic sea ice. This picture was taken probably about 150 miles from the North Pole, end of winter in 2020. We were taking part in an expedition called Mosaic. So Mosaic was the multidisciplinary drifting observatory for the study of Arctic change. It was a year-long expedition. It was an international effort. The German icebreaker Polar Stern was sailed up to the Arctic here in September of 2019. The sea ice froze around it, and then it drifted with the sea ice across the Arctic for a year. And so there were scientists on board looking at the atmosphere, the ocean, ice, biogeochemistry, ecosystems. I was on the expedition from January to April of 2020. So basically this chunk of the drift. And Gina and I were flying a different small drone, a Data Hawk. Groups or members of our team went after Gina and I came back after April and did some multi-rotor flights to do imaging of the sea ice. But we had team members flying from March to August of 2020. The winter leg that Gina and I were on was challenging. We had really cold temperatures. We had an anomalously cold March when we got up there, temperatures down to minus 40 degrees Celsius. We were also well in the center of the Arctic pack ice, a place that you don't expect to be particularly stormy in the winter. The storms are more on the edge, but we had multiple storms with winds in excess of 25 meters per second. In the middle of the pack ice in the winter, you expect that the ice is continuous. Because of all the storms, the ice broke up a lot. We lost instruments into the sea ice. This is the tent that Gina and I worked out of. This is the ship that we lived on. You can see multiple cracks in the sea ice that we crossed to get out to our camp. Every morning you'd wake up, you go up to the bridge, look out and see what the wind had done, what new leads had opened up, what you'd have to do to get out to your site. Okay, so the Data Hawk is bottom left here. It's just a foam plane. It's made by the Aerospace Engineering Department at the University of Colorado. It's launched with basically a bungee cord. So there's a couple of metal rails that angle up. There's a bungee cord that launches it. So I'll show you what one of these flights look like.
Okay, go. 3, 2, 1, go.
Just barely had enough to get going. That bungee cord doesn't have a lot of stretch when it's 30 below out. Yeah, so this is our first flight with the Data Hawk up on the sea ice in the Arctic. We're very happy when we finally got one in the air. Here are just some profiles of what the Data Hawk's measuring. So it again is measuring atmospheric state temperature, pressure, humidity, and winds. We have potential temperature profile. Here in the brown, we see a shallow, near neutral boundary layer with strong inversion above. Wind speed profile in purple with a broad low-level jet, a very common characteristic of polar boundary layers. And Gina calculated, pushed the number to tell us something about strength of mixing and vertical potential temperature gradient. So we had 89 Data Hawk flights from March to August. Gina analyzed boundary layer depth, stability, low-level jets with that data. But she also took the year's worth of radiosonde measurements from the Mosaic expedition and analyzed them the same way that McKenzie did, using a self-organizing map. Here, we had lots of profiles. So brown is a potential temperature anomaly profile. Lots of profiles with weak stability near the surface and then enhanced stability aloft. Varying depths of where that strong stability is, how strong it was, but also some strong surface-based inversions. So a little bit different looking than the coastal Antarctic sites, but more similar to that than the interior sites. Okay. And the last project I want to talk about is Caesar. So this one that Jen was on with Marley. So Jen and I were collaborators. So the project involving lots of different people. But this was to look at cold air outbreaks in the northern North Atlantic Ocean. So we have the Arctic ice pack, cold air forms over the sea ice or over Greenland. That cold air gets infected out over the northern North Atlantic. And then just like in Terra Nova Bay, what I started the talk with, that cold air flowing over warm water generates big upward sensible and latent heat flux. It generates clouds. It modifies the atmospheric state. So we use an NCAR C-130 instrumented aircraft to make measurements looking at these cold air outbreaks in the northern North Atlantic. We had 8 useful scientific research flights. Most of them sampled cold air outbreaks in various places in the northern North Atlantic, from near the eastern edge of Greenland up to Svalbard. We had one flight that looked at dust and impact on clouds, and we also had a flight where we looked at a polar low north of Scandinavia that formed in these cold air outbreaks. So we had 8 research flights, 54 flight hours, 114 drop-ons. Jen and I are working together, and obviously has Marley that's making continuous measurements of boundary layer state. I'm also using the drop-ons to look at the boundary layer state. So I'll just show you a few different research flights. So this one was on March 11th. This is the cold air outbreak to orient you. This is the northern edge of Scandinavia, so Norway and Sweden. This is Svalbard, archipelago, and then this is the eastern edge of Greenland. Sea ice is all up here. This is open water with clouds over it, and you see these cloud streets of cold air streaming down out of the Arctic, forming these convective clouds. The map shows where the drop-ons were dropped, and then up here is potential temperature profiles of the drop-ons going from near the ice edge to back out to near Scandinavia. And what you see is downstream warming and a deepening of the boundary layer as you move downstream, just like in the Terranova Bay flights. Yeah, so a very similar physical environment. This is a moderate cold air outbreak case. This one on March 16th, it's a strong cold air outbreak. You can see that cold air. So this is the edge of the sea ice. Cold air streaming out aligned with these cloud streets. Our flight flew out to the northwest up towards Greenland. You can see very cold temperatures, surface-based inversion, where we flew out over the sea ice and drop-ons. And then you can see the boundary layer warming something like 20 Kelvin over this distance as that cold air streams over the northern North Atlantic. You can also see the boundary layer growing in depth quite markedly. In addition, of course, there are clouds in there that are forming. So a lot of atmospheric dynamics, thermodynamics, cloud processes that are of interest with the data that was collected here. And then one other flight, this is April 2nd. Here, this is the southern tip of Svalbard and the northern edge of Scandinavia. There's a little swirl in the clouds here. This is a polar low. Polar lows are sort of like polar versions of hurricanes. They form in these cold air outbreaks when you get strong upward sensible heat fluxes. And so these are 2 images of the polar low 2 hours apart. You can see the little center with almost an eye-like feature. And then this is the flight path. So the black circles show the position of the center of the polar low over 6 hours. And then the flight basically crisscrossed back and forth across, just like the hurricane hunters do with tropical cyclones. So we collected a lot of interesting data in this polar low environment. And so it's a pretty infrequently sampled environment. So a lot of interesting data there to be analyzed. Okay, so my group is mainly interested in how the atmosphere interacts with other parts of the polar climate system, mostly sea ice and ocean. We've made observations over a wide range of polar conditions. So we've made measurements year round using drones, radiosondes, drop-sons. We've made measurements over permanent ice sheet locations, ice-free Antarctic regions, polynyas, Arctic sea ice, subarctic, North Atlantic, a lot of different environments. The late winter flights over Terranova Bay, we sampled hurricane-force katabatic winds and the modification of that dry continental air mass coming out over the open water of the Polynya. Our SuMO flights let us go to a lot of remote locations across the Antarctic continent and look at how the boundary layer evolves on sort of hourly timescales and measuring situations from very shallow, strongly stable to deep convective boundary layers. We used radiosondes to look at differing stability across the Antarctic continent, coastal and interior sites. We use self-organizing maps to objectively identify what all of those different profiles look like in about 20,000 soundings between the Antarctic and the Arctic. And then we have the drop-on data from CSER that will let us look at cold air outbreak, air mass modification, and polar low case. So I will leave it there with a picture of our SuMO circling over Pegasus runway at night. So the lights are, the wingtip lights and a time-lapse explosion.
Questions?
Yes. So during the polar night, you can still launch the small aircraft.
We can, yeah, so, we've done a lot of our drone flights in the winter. Because it's easy to fly them because there are no manned aircraft flying, so there's no one in the airspace. So the air traffic controllers just let us do whatever we want, which is pretty unusual for doing drone stuff anywhere else in the world. So other than it being cold and dark, it's a nice time to work. And scientifically, it's interesting because people usually don't make measurements in the winter in Antarctica because field work is hard to do. But it's the most Antarctic time of year, so it's really a good time to be there.
These are really fascinating measurements. Have you looked at how good the ERA analysis was operational analysis compared with your measurements?
So we haven't looked too much at the reanalyses. We've looked at forecast models, both in the Antarctic and the Arctic. And I've been surprised. So back in the late 90s, when I was a PhD student, I was involved in developing numerical weather prediction models to use in the Antarctic. And the model skill was pretty terrible back then. When you talk to Antarctic forecasters, they said, yeah, we have confidence in our forecast about 8 hours out into the future. And it's improved a lot since then. We've compared some of the drone flights, but a lot of the radio sound data with the models. And the models surprisingly reproduce the full range of stability profiles that I showed you in those self-organizing maps. They don't get them at the right frequency, but they simulate everything from the strong surface-based inversions to the shallow mixed layers with inversions above. They simulate all of that, and I was really shocked. So the models have come a long way. And I assume the reanalyses are similarly good. Yeah, it was a very surprising result, to be honest.
Just curious, if you, for your drone flights, if you set up the drone so it's flying straight and level, could you extract turbulence information from the variability of the vertical position of the aircraft?
We actually have, on the data hawks, we have a fine wire hot anemometer, and we extract turbulence from that. Yes. Yeah, those are hard measurements to make, but we do get turbulence intensity at the very least. You know, we were hoping that we would get turbulent heat flux as well, but I'm not really confident in the numbers we get. But the turbulence intensity we do get.
You might not get really accurate W prime or anything like that, but relative turbulence information.
Yes. Yeah.
Cool.
Yes.
Really strong convergence intrigue me. I mean, here in mid-latitudes, obviously we have a diurnal cycle, and
Yes.
you know, we get an inversion wintertime, and then it goes away and gusts. But in these polar nights, I mean, and yeah, you don't have solar, obviously, and I guess there may be some thin clouds. What I mean, what controls the magnitude of that? I mean, how cold can you get? I mean, what's the restoring force to actually, minus 30, minus 40, what's offsetting it? What's keeping it from getting just colder and colder and colder? Is it infection, cloud?
So it usually is clouds that will come in. So even a thin ice cloud generates a little bit more downwelling long wave radiation. So in those interior sites, in the extremely strongly stable cases, we see downwelling long wave radiation of about 70 or 80 watts per meter squared. That's all the downwelling long wave radiation you have. So basically you're balancing that with the upward from the super cold Antarctic ice sheet, and you get to radiative equilibrium with that basically space-like downwelling long wave radiation because it's cold and dry. The other thing that will break up that strong stability near the surface is if the winds pick up. So most of the continent is sloped, and so when you get that cold air, the katabatic winds start to go, and the colder the air becomes, the stronger the katabatic winds, and so they limit themselves. So the air gets cold, and then you get turbulence, and it mixes it out. Dome C is a dome; it's flat, and so there you get really, really cold temperatures.
So it's kind of related to the model. Seems like a model would struggle with that.
Yeah.
Temperature prediction to that magnitude, given especially the clouds and stuff. So
Yeah, it's a challenging problem, but the models are better than I thought they would be, to be honest.
Based on your time in both poles, which would you say is colder?
Antarctica by far. Yeah, so I haven't been in the interior of the continent in winter. But I've been McMurdo, I've seen temperatures, air temperatures down to minus 58 degrees Fahrenheit. I've seen wind chill temperatures below minus 100. Really nasty. Mosaic, the coldest temperature I saw were minus 40, and that is about as cold as you see at the North Pole. Because the sea ice, it's a couple of meters thick, and you get some heat flux from the ocean below, so there's a limit to how cold it gets. And minus 40 really was colder than we expected. I thought minus 30 would be about as cold as we say. So, yeah, Antarctica is definitely colder.
Great, I think we can continue the conversation in the lunch, right? After lunch, we have students instruction, so we can talk with them more. Right, okay, so let's thank John for one more time.
Thanks, everyone.